This is section 15.4 on gas laws. Here's our objectives: be able to state Boyle's law, Charles' law, and Gay-Lussac's law, and solve problems using those, and then also the combined gas law and do problems with that. Alright, so here's Boyle's law, and this was discovered by a guy named Robert Boyle. He lived between 1627 and 1691, and what he found out was that pressure and volume are related. And so you can see as he increases the pressure that the volume goes down. And I mean, that makes common sense if you think about it. But, you know, up until this point, they didn't know for sure that it was directly related. And so that's what Boyle proved, was that it is inversely related. You know, as one goes up, the other one goes down. So inversely related, you know, if I double the pressure, if this is 2 times, then the volume would be 1/2, and so on. And our formula, you can see, is pressure times volume equals K, and K is always a constant, so you'll see that a lot in here, but that just stands for a constant. In other words, if we're talking about a set amount of gas, a particular container that contains some gas, if you take the pressure times the volume, no matter what it is, it's always going to come out to be the same thing. Change pressure, you know, the volume change. Change volume, and the pressure will change, and so on. All right, so let's take a look at a kind of a little animation here. But you can see, you know, if we've changed the pressure on the left, you know, is 100 or 1, and on the right it's 1.3. And what we're going to do is we're keeping the temperature the same, but notice what happens to the volume. So you can kind of see here, and it kind of graphs it as it goes through. But that's, you know, that's Boyle's law. And notice that in this, you get a curved line, okay? You get a curved line here. You don't get a straight line. You get this curve. That's what inverse proportions give you. And if we want to use Boyle's law to solve problems, we would set it up like this. We would say, hey, our initial, you know, pressure and volume, well, is going to equal whatever we change it to. So P1V1 equals P2V2. So let's say, for instance, that if we've got an initial pressure of 101.3 kilopascals and volume of 2 liters, what's the new volume if we change the pressure? One of the things, because as we go through this, you'll see a lot of different problems. One of the things that I find is handy is if you write down everything that you're given so that you can figure out which formula you're going to need, because you're going to have about 5 different formulas eventually in this chapter, and it's really kind of hard sometimes to separate them. So it's always better if you just say, hey, what do I have? Okay, pressure 2 we know is 150 kilopascals, and volume 2 is what we want to try to figure out. Okay, so if you look, you know, you see that we have everything but the V2, and so we can solve it, put everything in there. So 101.3 times 2 equals 150 times V2. Okay, so I mean, that's pretty straightforward. Just do the math. Take 101.3 times 2 divided by 150, and you get 1.35. And then what the label for this would be whatever the label for the other volume was, so it would be liters. Okay, and one of the things to think about is, does it make sense? Okay, so always think about it. Okay, I've increased the pressure, and I got a smaller volume. Does that make sense? Yeah. Okay, that's very possible. All right, Charles is another one that, and this was discovered by a guy named Jacques Charles, and he was working with volume and temperature. And what he found, notice that we've got a straight line here, and he found that there is a direct relationship between volume and temperature. If I double the volume, so 2 times the temperature, and usually we're changing the temperature. If I change the temperature, twice the temperature, I'm going to get 2 times the volume. Okay, so he's saying that volume is directly proportional. When you see something that's directly proportional, that gives you a straight line. As one increases, the other increases. 3 times the one, 3 times the other. And when we write it, though, if you think about it, it has to be a fraction. As I double this one, you know, this one's going to double. so that it always equals the same thing. K, once again, is another constant that we have. You can see our formula is V1 over T1 equals V2 over T2. Remember, temperature must be Kelvin. Has to be in Kelvin temperature, or this law is not, it doesn't work. You can't end up with negative volumes. So let's do an example. Okay, a gas has a volume, so let's write that down, V, volume 1, of 500 milliliters. Temperature, 0 degrees Celsius. What's the volume? Volume 2, we don't know. At 200 degrees Celsius. Now remember, first thing we got to do is change to Kelvin. So add 273 to both of those. And now we can do the problem. So we can say 500 milliliters over 273K equals our unknown volume over 473K. And you can just do, I always call it cross multiply and divide. I think you guys call it a lot of times the butterfly method, but you're just going to take 500 times 473 and divide by 273. And you get 866. Once again, just double check that a little bit, because it's common that you might flip around, especially when you have to do solve for ones in the denominator. A lot of times you guys have problems with that. So make sure you check it out. Does it make sense that if I increase the temperature that the volume is going to go up? And yeah, that makes sense. All right, the third one of these is Gay-Lussac's law, and he studied temperature and pressure. So, we've talked about volume and pressure and temperature, so here's our third possibility. And he found that they are directly proportional. So this is going to be like Charles' law, directly proportional. You're going to get that straight line. Also means you have a fraction. So that's what directly proportional is always telling. So I'm going to take pressure over temperature. That's going to give me a constant. So I'm going to get P1 over T1 equals P2 over T2. The problem works the same way as Charles' law, so I'm not going to do another one of those right now, but it's the exact same kind of thing. And whenever you do these problems, you're going to get 3 out of 4 of those variables, and you have to solve for the fourth one. Or we're going to put them all together, and then you'll get 5 out of 6 of the variables. So that's known as the combined gas law. And we can take all of the previous ones and we can kind of put them all together. We can kind of combine them all. And when you do that, you get this law. And I can't really type it very well, but it's better if you kind of see it. So it's P1V1 over T1 equals P2V2 over T2. So in the combined gas law, there are 6 variables. You will be given 5. Now, sometimes you might say, oh, well, they might say the temperature is constant. Well, if that's the case, get rid of the temperature. And look at what you got. You got Boyle's law. Okay? Or sometimes they might say, hey, we're going to hold the pressure constant. And if that's the case, get rid of the pressure. And there you have Charles' law. So you can just see that all of the laws are in here. Just put all together. So to be honest, I usually just remember this one formula, PV over T. And if I remember that, I can get the formulas for all of the other ones that we've talked about previously in this section. All right, let's do an example. And this is why I think it's important that you write down what you have, because sometimes you'll use Boyle's law or Charles' law, and sometimes you use this whole law, and then sometimes you'll use another law that is similar to this, which we'll get into in the next section. And it's just so much simpler if you start writing down what you got. I got volume 1, 400 liters. Temperature, oops, that should be a degree sign. Temperature 1 is 20 degrees Celsius. Pressure 1 is 300 millimeters of mercury. Now, normally, I prefer that we use the SI term, which is kilopascals, but sometimes they give you the problem in various things, and you have to figure it out. One of the things that you may not know, though, for STP in terms of millimeters of mercury is 760 is standard pressure. Okay, so we're going to need that. So we know now, we're trying to find volume 2. We don't know that one. And we do know the temperature 2 is going to be standard temperature, which is 0 degrees Celsius, and standard pressure, which is 760 millimeters of mercury. So we know our formula, P1 V1 over T1, so we're looking at PV over T. So let's put pressure 300 times V 400 over T. Now make sure that you convert this. So that's going to be 293. Got to convert it to Kelvin every time. That's the thing that you have to remember. That's the most common mistake that everybody makes. Okay, 760 times V2 over 273. And then you just do this. Now, what I usually just think of is I'm going to take this times that, and I'm going to divide by these guys here. Okay? So, how I do it on my calculator is I go 300 times 400 times 273. All those things get multiplied, and we're going to divide by 760 and divide by, you got to push the divide sign again, 293 equals. And I get 147. And once again, the label is going to be whatever it was here, which is liters. 147 for the volume. And does it make sense that the volume would go down if you increase the pressure and decrease the temperature? Sure, makes sense. Now sometimes you can't always reason that out, because if you might do one that increases the volume and then another thing that decreases the volume, and that so you can't really tell. But it is always a good idea to check, see if you can. Alright, so that's the end of that section. So 4 new laws really, but if you just remember the one, PV over T, that will give you all of the information. You can always kind of cover up the one you don't have or erase the one you don't have, and you'll get the other ones.